Good morning, everyone. If I could get your attention, please. We have taken a few moments just to sort out a few issues. Now we are ready to get going. It's wonderful to see an audience like this. Obviously, a lot of people here have been here all week and know IYPT very well. But I know there's a lot of students around in this room and in another room, and we're being streamed on the web, so hopefully lots and lots of people are going to see the wonderful performances of our teams today. Just to try and set the scene, not all of you have been here for the tournament. The International Young Physicists Tournament is a research-based tournament. 17 problems were set a year ago. Our teams have been trying to find solutions of them for the whole of that year. They have arrived at this tournament and they have performed 3 roles, and that will be shown by the 3 teams that we have on the stage today. Each role is slightly different. There will be the role of the reporter who presents their solution. There is the role of the opponent who critiques the presentation of the reporter, weighs up the good and the bad, and tries to test how good that theory is. And then the reviewer steps up and tries to sum up what went on in the fight. At that stage, we will come to the people sitting at the front here who are our jurors from all over the world, and they will ask a few questions to clarify things, and then they will grade the reporter role, the opponent role, and the reviewer role. Each juror will give a mark out of 10, and this will lead to their scores as the fight goes through. We then go to a second stage where they change roles, and then a third stage where they change roles again. So they will have done all 3 things: report, oppose, and review. During our 5 selective fights that these teams have navigated their way through to get to this point, there was, in most of them, a challenge role. That is omitted in the final, and our 3 teams are presenting problems of their choice. Problems of their choice. So if we go on and meet the people that we have here today, on stage we have a team from China, and we'll get some introductions in a moment. We have a team from Poland, and we have a team from Singapore. In the first stage, the team from China will be our reporter, the team from Poland our opponent, and the team from Singapore our reviewer. So to start the whole process, can I ask the captain from Team China to introduce your team?
So good morning, ladies and gentlemen. We are a team of China. This is Wang Jingxian, Cong Guanghe, Gong Zhenyan, Yi Jiahong, and I'm Lu Kehan. Hope we can have deep and inspiring physics fight, and we promise it is worth getting up so early today. So thank you.
Thank you very much. And the team from Poland?
Good morning, ladies and gentlemen. I'm the team captain, Radus Waszkiewicz. This is Bartek Marchiński, Ania Wald, Fredrik Grabowski, Oskar Grudzyński. We are a team of Poland. We wish for a pleasant and meritorious fight.
Thank you. And finally, our review team from Singapore.
Right, good morning, everyone. We're from Singapore. This is Yu Zhe. I am Jin Ming. This is Yu Jun. This is Jin Hing. And this is Whitman. And here's our mascot, Mark the Monkey. Thank you.
And as I say, our other layer to the tournament is having respective physics teachers, physics researchers from all over the world who are going to be scoring our teams today. And I would like to go along the line and ask each member to introduce themselves. So when you're getting up, switching the microphone on and switching it off when you finish.
Hello, everyone. My name is Andrei Klishin, and I represent here Team USA and MIT. And I wish that all the teams show us today the best they got. Thank you.
Good morning. My name is Florian Ostermeier. I am from Germany, and they're coordinating our national tournament, the IYPT.
Good morning, everybody. My name is John Balcombe. I'm a physics teacher from Shrewsbury School in the UK, which was last year's tournament took place. Thank you.
Good morning, everyone. I am Felicia Ulstad. I'm a former participant from the Swedish team a few years ago, and well, I hope you have a very nice fight today. Thank you.
Good morning, everyone. I'm Yongyuan Xu from Taiwan. I hope everybody enjoy the flight.
Hello, my name is Ilya Marchenko. I was a participant myself 14 years ago, but right now I have a PhD and my area of interest is experimental soft condensate matter physics. I would like to wish all teams an outstanding competition and a very memorable experience at this finals.
Good morning, everyone. My name is Catherine Zealand. I was a participant in IYPT about 10 years ago and involved with the Australian team ever since.
Hello, my name is Martin Pleš from Slovakia. I was a participant very long time ago, but I still can remember how exciting and nice it is to stand on such a stage. So I wish all of you very nice fight and all of you nice experience.
Good morning, everyone, and สวัสดีค่ะทุกๆคน Narumon Suranaree from Chulalongkorn University. I wish you all the best today. Sorry.
Good morning. My name is Kent Hogan. I am a team leader from New Zealand. I'm a physics teacher at Onslow College, and very good luck to all the teams.
Good morning, everybody. I'm Valentin Lobashov, professor of Moscow State University, Russia. I participate IYPT just from the beginning, and I wish the teams good luck.
And to introduce myself, my name is Alan Allinson. I'm a physics teacher from Brisbane, Australia. And before anyone worries, I will be a non-voting chairperson. I don't get to vote, so I just get to enjoy watching the tournament. I don't have to think in great detail about it. I've also had the pleasure of being president of IYPT since 2008, and I've seen some wonderful fights in that time. I'm really looking forward to seeing it again today, and I wish you all very good luck and hope it goes your way. So we move on to starting the first stage. For those of you who are new to the event, we have a clock on the left of the stage which will run down the time that they have for their various roles. In normal situations, they will have a challenge and they will get 1 minute to challenge. This is shown on the screen at the moment. We need to advance it to the point where it says we have 5 minutes preparation time because our teams have already chosen their problems. And so, team from China, you have 5 minutes to prepare. Good luck. Okay, we're just about ready to start. Can I ask the three people who will perform in the stage, when they first enter the stage, clearly introduce themselves to everyone else, and we don't need to record it quite the same way as previously, but please make it clear who you are and who you're representing, and good luck.
Good morning, all the jurors and my dear opponents and the reviewers and all the audiences presented. I'm Gong Zhenyan from Chinese team, and I'm the reporter of Liquid Film Motor. So let's first see the outline. First, I will introduce introduction, and then the theoretical analysis, then the experiment, and finally, I will reach the conclusion. So first, in the introduction, I will first review the problems and the preliminary experiment. So first, let's review the problem. Form a soap film on a flat frame. Put the film in an electric field parallel to the film surface and pass an electric current through the film. The film rotates in its plane. Investigate and explain the phenomenon. And the key word are film and rotate. And the task we're going to do is to explain and investigate. Okay, then let's see the preliminary experiment. So let's first see the preliminary experiment setup. You can see these are two polar plates and these are two electrolysis electrodes. And here's a tiny film and here's a CCD camera to record the rotation. And in next experiment, we'll use the CCD camera to get the BMP picture, and we'll use the pixels in the BMP picture to get the velocity of the rotation. And maybe this is not quite clear, and here's the schematic. You can see these are two polar plates, and these are two electrolysis electrodes, and here's the film. And in the preliminary experiment, we use 30% glycerin, and also this slide view, we tilt the film a little bit to eliminate the effect of the gravity. So let's see the phenomenon. I guess you can see it quite clearly. You can see the colorful film, which is caused by the film interference and the rotation. Okay, so let's move on to the theoretical analysis. In the theoretical analysis, I will try to solve three problems. First, why can it rotate? And when can it rotate? I mean, the criteria for rotation. And how does it rotate? I mean, the kinetic equation for rotation. Okay, so let's first see why can it rotate. Since I put an external electric field to it, based on the a problem in IYPT 2012, the floating water bridge, it has implied that in the external electric field, a linear branched chain-like structure can form in the water. You can see in this picture, these are chain-like structure. And this transforms the Newtonian fluid to Bingham-type plastic fluid. And all of my theory will based on this Bingham-type plastic fluid. Okay, this is another function of the external electric field. I believe when there is no external electric field, you can see the dipoles are completely random in the film. And when I apply the external electric field to it, it will cause the polarization equilibrium. And here's the equation for the polarization equilibrium. Okay. So then I apply a current to it. Since first it gained a polarization equilibrium, which means the positive charge will accumulate this way, which means it will have a constant positive charge and negative charge here. And since I add a current to it, it will cause the charge to migrate this way, which means it will have a constant driving torque on the film, and this causes the rotation. And here's the equation for the driving torque. Okay, so this explains why it can rotate. So let's see when can it rotate, the criteria for rotation. Since we got the driving torque, then if we can have this dragging torque, then we can use the torque equilibrium to get this equation. And since I use the Bingham-type plastic fluid and the static resisting moment comes from the yield stress. So here's the static resisting moment. And then I can get this equation. For the same type of the liquid film, the tau zero, which is the yield stress, is constant, and the epsilon, which is the permittivity, is is also the constant. So for the same type of the liquid film, this is the constant. So which can simplify to this equation, which means the strength of the external electric field and the voltage of two electrolysis electrodes should reach a threshold, then it can start rotating. So then let's see, how does it rotate? So first, we consider the yield stress, which is here, and the viscous force, which is here. Then we can get this dragging torque. And then we use the driving torque and the dragging torque to get the resultant moment, and then we apply differential to it, then we can get the resultant moment in each circle. You can see here, we use a lot of circles in this liquid film motor. And then we use the Newton's second law of rotation and the new resultant moment we get to get this new equation. The ut is the first derivative of the velocity. But since it has relationship with the time, so we solve this problem using when r is 0, the velocity is 0, and when r is equals to the radius of the liquid film, it is also the 0, and when time is 0, the velocity is also 0, and we assuming that the time is unlimited, which means it achieves a stationary condition. So then we can get this equation. We can see that the higher the viscous force, the lower the rotational speed, and from in the center of it, it can reach the highest speed, and away from the center, the speeds become lower. Okay, so let's do the experiment. So first, based on the rotational threshold, we change the proportional glycerin, which we believe it will change the tau zero, which is the yield stress. And also for the rotational speed, we tested the angular velocity distribution and external electric field and electrolysis electric field and dynamic viscosity. Okay, so let's first see the rotational threshold. We set some of the external electric field as constant, and we elevate the electrolysis electric field. When it starts rotating, we record the figure of the electrolysis electric field. And here's the figure we obtain. Here's the logarithm external electric field, and here's the logarithm of the internal electric field. And from this figure, we can see it matches to our theory very well. And we can also see that the higher the proportion of the glycerin, the lower the threshold. We can see here it is 30%, 50%, and 70%, and the threshold becomes lower. And here's the theory line. We can see we use the tau zero as 10 to negative fourth. And then is the rotational speed. First, I tested the distribution of the angular velocity, and I tested under the electrolysis electric field is 50 voltage, and the external electric field as 200 voltage. And here's the figure. We can see near the center of it, it achieves the maximum angular velocity, and away from the center, the speed becomes lower. And here's the theoretical line, and here's the experimental line. We can see although the experimental line is a little bit higher than the theoretical line, which I believe is caused by the error of the CCD camera, but the trends matches the theory line very well.